Hello, everyone. Welcome to the lab on projectile motion. So basically, the way that we're going to run the rest of these labs is I have gone to Springfield College and I collected a lot of the data for you. So I will give you that data, and I made videos so you can see how I actually collected all the data. So you will be analyzing data, creating graphs like you normally would with lab reports. And also, I'm going to use some computer simulations, and you can get data from the computer simulations and analyze that data as well. So between the data that I collected and computer simulations, we should be able to get a good understanding of the concepts. And the way that we're going to submit labs, they're going to be group lab reports, just like they were when it was an in-class session. You want to keep the same exact groups that you had when you were working in class. So it's up to you guys. I know some of you like to use Google Docs, or you may want to share Word files, however you want to do it. You want to make sure that everyone contributes to the lab report. And then one person, you just need to have one person from the group, from your lab group, submit the lab report. So I'm going to have it set up in Brightspace under assignments, and you can upload your lab report under assignments. Okay, and all the content, all the videos will be posted on Brightspace as well under the content, so the usual content tab. Okay, so let's talk about projectile motion. Okay, so projectile motion. So you can think of this, let's say we have a gun, like basically we use a spring-loaded gun in lab to launch marbles. So let's say that the marbles are launched some particular height. I'll draw this vector. So this vector is the initial velocity that the ball is launched at. And typically what you should do is you should find the components of that initial velocity. So if I make a little XY coordinate system here, then if I project down right onto the x-axis, this is going to be the x component of my initial velocity, so I'll call it v naught x. And if I project over to the y-axis, this is going to be v naught y. So v naught means the initial launch velocity, v naught x is the x component, v naught y is the y component. And we know what's going to happen in general with a projectile, right? So if I launch this, it's going to do something like this, right? It's going to go up, reach a peak, and then come back down and hit the ground over here somewhere. Okay, so assuming that there's no air resistance, then in the x direction, there are no forces acting, right? There's no forces acting in the x direction. If there's no net force in the x direction, that means that the acceleration in the x direction is 0, right? F net equals ma. So if the net force is 0, the acceleration in the x direction must be 0. Therefore, what's true about velocity? Well, if the acceleration is 0, the velocity must be constant in the x direction. So whatever I had initially for my v naught x, that's going to be the same component, same x component throughout the entire motion, including at the peak here. So I'm going to draw these all the same length. So the velocity in the x direction is constant. Okay. Now, what about the y direction? Well, are there forces acting on the ball in the y direction? Ignoring air resistance again. Yes, the force due to gravity, right? The gravitational force, which is the weight of the ball, is acting in the y direction. So in the y direction, we have free rise, free fall motion, right? Remember, any object, if you throw it up in the y direction, it's only acted upon by gravity, then it undergoes free rise, free fall motion. So initially, we have this large velocity in the y direction, that v naught y. But then at this point, it's going to be still upward but smaller, right? At this point, still upward but smaller. At the peak, there's no velocity in the y. It's all in the x. And then after the peak, it'll be small negative, then more negative, and so on. Okay, so you can think of projectile motion as consisting of two motions: constant velocity motion in the x direction and free rise, free fall motion in the y direction. And if you put those two together, you get the motion of a projectile. Now, the other thing that's going to be really important is something called the range. Okay, so if I look at this, certainly this distance right here, from here to where the ball lands, that is some particular horizontal displacement, right, between those 2 points. But there's a very special horizontal displacement, and it's defined to be from the point of projection, so the point of projection, which is right here, I'll do it in red, to a point on the path that's at the same elevation as the point of projection. So if I go to the path, the same elevation, same height, that'd be right here. And that distance, that horizontal displacement that's at the same height, this is called a range. Okay. And what we want to look at in today's lab is if we change the angle of the projectile, so the angle theta here is the launch angle. If we change that angle, if we vary the angle, how does it affect the range of the projectile? Okay, so it turns out that you can derive a formula for the range. Let me show you that. So the range, which I'm going to call R, is equal to V naught squared sine of 2 theta divided by G, where V naught is the launch velocity or launch speed. Theta is the launch angle. So launch angle. And then G, of course, is the acceleration due to gravity. And G, it depends on what units we're using. For the first part of the lab, when I actually collect the data, we're going to use CGS units. For the second part, where we look at the simulation, we're going to use SI units. So G is either going to be 980 centimeters per second squared or 9.8 meters per second squared. Okay, so it depends on what units we're using, but it's a constant, right? It's acceleration due to gravity. So therefore, there's several things that can affect the range, right? If we increase the launch speed, so if we make this term right here larger, then that's going to increase the R value, right? If V naught becomes larger, R becomes larger. It's also going to be affected by the angle theta, by the launch angle. That's a little more complicated because it depends on the sine function, okay? And that's what we're going to look at in lab very carefully today. And it also depends on G. Now, obviously, G is pretty much a constant on the surface of the Earth. But if we were to do this experiment on, say, the moon, where G is a lot smaller, it's around a sixth of the gravity compared to that on Earth, then the range would be 6 times as far, 6 times as large, right? So it really depends on G as well. But for our cases, since we're launching everything on the surface of the Earth, G is going to be just a constant. So the V naught, the launch velocity, is going to depend on how strong the gun is, right? It depends on the spring in the gun itself. So we're going to measure that, but for each gun, that's going to be a constant, right? So for your data, basically, it's going to be a constant. So really, the range here is going to depend on the angle theta. So So as we vary theta, it's going to affect the range. And that's really what we're interested in. How does the range change as that angle theta changes? Okay, let me go back up here for 1 second and show you one more thing. So if you wanted to find these components of the initial velocity, then you could simply do that using trigonometry, right? So here, I'll come back down. Oops. Do that. Let me blow up that little piece. So if this is my launch velocity, here's my x, y coordinate system, and I want to find v naught x and v naught y, and I know that this launch angle is theta, then you could extract, right? You could extract this right triangle that contains the angle theta. So the hypotenuse, right, is just the magnitude of that launch velocity, which is the speed, the launch speed, so v naught. And then this is theta, this is v naught x, this is v naught y. So therefore, if I want to calculate v naught x, I know since v naught x is adjacent to the angle theta, then I would use cosine, right, ca. So cosine of theta would be the length of the adjacent side divided by the length of the hypotenuse. And then if I multiply both sides by v naught, I'm going to get that v naught x is equal to v naught times cosine of theta. And then if you make a similar argument for v naught y, well, since it's opposite of the angle theta, and we also know the hypotenuse, which is v naught, then I could use the sine function, right? So sine is opposite, so v naught y over hypotenuse. So if I want to find v naught y, I would multiply both sides by v naught, and I'm going to get v naught times sine of theta. So if you know the launch speed and you know the angle, then you can easily calculate the components. And like we were saying earlier, this value, the x component, regardless of where we are on the path of the projectile, that's always going to remain the same. That's going to remain constant. The v naught y will change, or sorry, the vy will change. The v naught y is the initial velocity in the y direction. So the vy will change, but the vx at any point on the path is equal to the initial velocity in the x direction. Okay. Okay, so let's look at the lab report handout itself to see what we need to do for this particular lab. So the first page is just some of the background information I already went over. Right? The range formula, very important. Okay, so for the first part of the experiment, the first thing that we need to do is we need to determine the launch velocity of the ball, right? The speed at which the ball leaves the gun. So to do that, well, we know that velocity in general, we can think of as the change in position over change in time, right? Displacement divided by change in time. And in this case, we know the time that it takes the ball to pass through the photo gate. There's a photo gate mounted on the end of the gun. So the displacement is simply going to be the diameter of the ball. So if we take the diameter of the ball and we divide it by the time it takes that diameter to pass through the photo gate, then that gives us a very good estimate of the velocity when it's leaving the gun. Okay. So first thing you guys want to do is you want to watch my video on how I actually collected this data. So I show you how I collected the time for the ball to pass through the photo gate. And I also showed you a little bit on how to collect the range data. Right? So make sure you watch that video just to get an idea of how we actually collected this data. Okay, so the data for the diameter is just 1.90. That's given here in the table. And these are the 3 times that I got when I launched the ball at these 3 angles of 15 degrees, 45 degrees, and 75 degrees. And you can see that the times are fairly equal. They're pretty much the same, right? And in theory, they should be just about the same. So question 1 is simply for you to calculate the launch velocity or launch speed of the ball for each angle. So all you have to do is divide the diameter divided by the time, right? And get that launch velocity. So do that for all 3 angles here. And then you want to average them. So average those 3 values, and that's going to be your launch velocity of the ball. Okay, so and make sure you show me all those calculations. So calculate the 3 velocities, average them together, and that's going to be your launch velocity of the ball. We'll assume that that's constant. Okay, next, here's the range data. So again, make sure you look at the video to see how this was collected. Basically, I measured the distance from where the ball landed on a piece of paper. I left a mark. We had a piece of carbon paper on top of a piece of white paper, so it leaves a mark. And I measured the distance in centimeters from that mark to the edge of the gun. And that's going to be the range. And I did 3 trials for each of those angles. Okay. Now, for 0 degrees and 90 degrees, it turns out that the range is 0. Actually, let me explain this more carefully. Okay, so why is the range 0 when the ball is launched at 0 degrees and at 90 degrees? So let me draw this out. So if a projectile is launched at 0 degrees, that means it's launched horizontally. So this would be the launch velocity. And what's going to happen to the projectile? Immediately, it's going to fall, right? It's going to be accelerated downward by gravity, so immediately it's going to start to fall. Therefore, remember the definition of range. It's the horizontal displacement from the point of projection to a point on the path that's at the same elevation as the point of projection. But since it immediately starts to fall, it never gets back, right? It never gets back to that particular height because it immediately falls. So therefore, when the angle is 0, when theta is equal to 0 degrees, the range is going to be 0. In this case, 0 centimeters. Right? Because it never gets back to that same elevation because it immediately starts to fall. And then the other case is if I launch a projectile at 90 degrees, so this would be 90 degrees, right, straight up, then what's going to happen? Well, projectile is going to go up, come back down on itself. And what is that distance from when it leaves this point to where it lands? Well, the horizontal displacement here is again going to be 0. So when theta is equal to 90 degrees, the range is also 0. Okay, so 0 degrees it's 0, and at 90 degrees it's 0. Okay, so hopefully that made sense, right? At 0 degrees it's 0, and at 90 degrees it's 0. So then at the other angles, at 15 degrees, at 25, at 35, 45, 55, 65, and 75, I did 3 trials where I collected those range values. And these are the data that I collected. So what you need to do, and this is question 2, is you want to calculate the average range for each launch angle. So you want to find these averages, right? So you're just going to average over these 3 values at 15 degrees, average these 3 values at 25 degrees, and so on, right? And for this part, instead of showing me all of them, maybe show me 1 or 2 sample calculations for each of those averages. Okay, then what you want to do is you want to plot range versus average angle. So the range will be plotted on the y-axis, and the average angle will be plotted on the x-axis. And you want to do this using Pascal capstone. And I'll show you this in a second. Using the coordinate tool, again, I'll show you this in a second, you want to locate the peak of the fitted sine curve to determine the experimental maximum range and the angle at which it occurred at. And the angle we're calling the experimental optimum angle. And then once you have those two values, you can fill in this table below. And then you want to compare those two. So compare the optimum angle theory with the optimal angle experimental by computing a % experimental error. And we already know that in theory, so theoretically, if we ignore air resistance, then the optimal angle, the angle that will give you the largest range, is 45 degrees. Okay, and you can see that from the range formula. 45 degrees will give you a maximum range. Actually, let me stop for a second and explain that point. Okay, so let me try and explain why 45 degrees would give you a maximum range, right? Again, assuming there's no air resistance. So if we start with the range formula, we know that R is equal to V naught squared sine of 2 theta divided by G. Now, V naught really, in this case, is a constant, right? Because V naught depends on the strength of the gun. It depends on how strong that spring is in the gun. So it's really a constant, right? It doesn't vary at all. And G, of course, doesn't vary. It's the acceleration due to gravity. In our case, we're going to use 980 centimeters per second squared since we're in CGS units. So the only thing that can vary is the sine of 2 theta, right? Is the angle. So that's the only term that can really affect the range here. So if we want the range to be a maximum, R max, then that means we want this to be a maximum. We want sine of 2 theta to be a maximum. All right, so let's think about what that function looks like. So if we graph out sine, so let's say I have, I'll call this X, I'll call this Y. And let's say I want to graph Y equals sine of X. Well, it's going to look something like this, right? It starts at 0, and then it's going to oscillate. And of course, it goes on forever in both directions, but I'm just going to consider one oscillation from like 0 to 2 pi. All right, and we know that the largest that this value can be is 1. So at the peak here, it's 1. And the smallest it can be is -1. And at 0, it's equal to 0. At 90 degrees, that's when it's equal to 1. It's 0 again at 180. It's -1 at 270, 0 again at 360, and so on. Okay. So again, right, let's go back to the top. If we want the range to be maximum, right, we want to maximize this value right here, then we have to maximize sine of 2 theta. But sine of 2 theta, like the sine function, varies between -1 and 1. So if we want this to be a maximum, then we want this equal to 1, right? If you look at this this graph here of the sine function, the largest it can be is 1. So we want it to be equal to 1. So when is sine equal to 1? It's equal to 1 when the argument, when x, which is the argument, is equal to 90 degrees. But in our case, the argument was 2 theta, right? Because we had sine of 2 theta. So when 2 theta is equal to 90, then we know that sine of 90 is going to be equal to 1, right? So therefore, what is theta? Well, if I divide by 2, theta is 45 degrees. So here, let me explain this one more time here at the bottom. So I have R equals V naught squared sine of 2 theta over G. So if I want this to be a maximum, R max, then I want my angle to be 45 degrees. Right, so I have 2 times 45 divided by G. But then this term, this is sine of 90, that's just equal to 1. So that means my maximum range is equal to, I can just write it as V naught squared over G, right? Because times 1 isn't going to change it. And later on, when you're asked to calculate the theoretical maximum range, that's the equation you want to use. So I'll call this R max theory. Okay, great. Okay, so again, we know now that the optimal angle theory is 45 degrees. So we need to figure out the optimal angle experimental. So let me show you how you can do this using Pascal capstone. I'll do an example for you. Okay, so here is our Pascal capstone. I want to go to the graph. What you can do, this is like a newer version, but if you go to classic templates, then we'll see the original templates that we're used to. So remember the upper left-hand one with the table and the graph, it's probably the easiest to use. So I'll click on that. Now for measurement, select measurement, go to create new, user enter data, just like we've done before. And in this case, I want to plot angle. And I want my units to be degrees. By the way, to get the degree symbol, if you hold the Alt key down on your keyboard, and on the numpad you press 2, 4, 8, and lift up the Alt key, it'll give you a degree symbol. If you don't see that, if you can't find it, that's okay. Just write in degrees. That would be fine. Okay, so the X is going to be angle, and then the Y, create new, user enter data, that's going to be range. I'll hit tab, and in units, for this part of the experiment, it'll be centimeters. Okay. Okay, so let's fill in our data, and I'll make up some similar data. So let's say 0, 15, 25, 35, 45, 55, 65, 75, and 90. Those are my angles. And then let's say my range values were 0, 42, 68, 87, 96, 85, 72, 40, and 0. Okay, and you will plot the ones that you will plot your averages. Remember, you have to find the average of the 3, and you're going to plot your averages here. Okay, so to do the graph, remember the x-axis is angle, so we're going to choose angle here, and the y was range, so I'll choose range in centimeters. So that's my graph. We want to get rid of those line connections. So remember, hover over data point, right click. If you have a Mac, sometimes you have to do control right click, and then uncheck show connecting lines. And then for the fit, for this particular data, it should be a sine, right? The function should be a sine. So if you go to the fit, go to the triangle part, you want to go down to where it says sine, and then it gives like a general form, sine of omega x plus phi plus c. So that's the one you want to choose. Hopefully it does a decent fit. Actually, that's pretty good. So there's our sine fit. Okay, now for the title, remember it's always y versus x. So in this case, it'll be range versus angle. And here's the part that's new, right? We want to locate the peak of this curve. So we did our sine fit, and we want to find the peak of our curve right here. We don't want to use our data points. We actually want to find the peak of the fitted curve. Then we'll have our experimental maximum range, or you can read off that value on the y-axis, and we'll have the angle at which it occurred at, which is the value from the x-axis. So the easiest way to do this is to use the coordinate tool. So if we click on the icon next to the fitting icon, this one right here, and you select add coordinate tool, then we need to do one thing. You need to change the settings on here. So we have to right click on it, oops, actually click on it, then right click on it, go to tool properties, go to coordinates, and let's change the snap to pixel distance to 1. So we'll just make that a 1. That means we'll have more fine control over it. It won't jump to one of our data points. We can actually set it at the peak of the curve, which is what we want. So I'll hit OK. And now I'm going to click on that coordinate tool. Whoops. We do that. Click on the coordinate tool and drag it. Doesn't want to drag. Hold on. There it goes. Drag it to the peak of my curve, which is pretty much like probably right there, be the peak of my curve. So now this value, this 94.5, that's going to be my experimental maximum range, right? That would be like my range value, the Y value here. And then the X value, which is our angle, theta, that's going to be your optimal angle experimental, 45.11. So this is what you want to compare, 45.11 to the 45 degrees when you're comparing the optimal angles. And then later, you're going to need this value. This is your experimental maximum range, the 94.50. And then do what you normally would do, right? Go to the side, copy display, and then paste it into your lab report. So when you submit it, I want to make sure that you have these graphs in your lab report itself. Okay, great. Okay, so now that we have that graph, then again, you can pick out the optimal angle experimental, compare it to 45 degrees by computing percent experimental error. Make sure you show me this calculation. Okay, question 4 is, well, first of all, if you go to the table here, the maximum range experimental, that is the range value from that graph, right, that we found previously. So that's from the graph. And then the max range theory is what I described in the other video. Remember, that's when theta is 45 degrees. So sine of 2 times 45, sine of 90 is just 1. So you're just going to use this formula here. For the maximum range, it's just your launch velocity, which you have here from your table. Right? Just use your average value there. You need to square it and then divide by 980. And that will be your max range theory. And then finally, you want to compare this value, your max range theory, to the value you got from your graph by computing the percent experimental error. Okay, so that's it for the first part of the lab. For the second part of the lab, we're going to use a simulation created by this group, this physics research group at University of Colorado Boulder. They have some really nice simulations here, and one of them is projectile motion. So this is the link that you need to get there. I will also post this separately on Brightspace. Okay, so let me show you this simulation. Okay, so here is the projectile motion simulation. So to start this, you could either download it to your computer if you want it on your computer itself, or you can use it right on the web here. So if I click on this, click on the play button, it should load it up. And in this case, we're just going to use the intro part. So if you click on intro. Okay, now a couple of things. What we want to do is we want to, since we're interested in looking at the range, the launch height has to be the same as the landing height, and the landing height is always on the ground here. So we have to lower this cannon so that it's starting at 0 meters. So its initial height is 0 meters. Okay, you're going to vary, this knob will allow you to vary the speed. I think I have you guys set it for 18 meters per second. Right now, I'll just leave it at, and I'll do like 15 or something for now. And then I want you to do a launch at 25 degrees, at 30 degrees, 35, 45, 40, 45, all the way up to 65 degrees. Okay, and fill in that data table. So for those angles, I want you to figure out the range. So the question is, how do we get the range? So let me do a launch. I'll just do it at 45 degrees. And again, you're going to use 18 meters per second, but I'll show you what this looks like at 15 meters per second. So to launch it, all you have to do is press this red button here. Make sure, by the way, that there is no air drag. And if you want to see the velocity components, you can do that. I can show you that in a bit, but you don't need that for this part. So you're going to do a launch. It'll fire the ball. Actually, I think it's a pumpkin now. Let me change this to, let me change it to a cannonball. Okay, but it should give me the same, since there's no air resistance, it should give me the same path. By the way, if you want to erase the path, just press this eraser button, the yellow one. So launch it. There's my cannonball. And now to measure the range, I'm going to take this tape measure. I'm going to put the first part at the cannon. So somewhere right around there. And then you can pull out the second part, the tape measure, to where it lands. Say right there. And if you read out that value, so in this case, 22.9 meters, that is my range, right, for that particular angle. Okay, so you're just going to do that for a variety of angles, starting at 25 and going up by 5 degrees all the way to 65. So in this case, that would be the landing point. So now you can leave the tape measure there, right? I just need to drag this part to here and then measure that value. So 17.61. So I'm measuring the range for each particular angle, just like we did in lab, but now it's using the simulation. And then if you want to, there's a couple of fun things you could do here. If you want to play around with the, let me clear this. Say the velocity vectors, components. Actually, let me do this in slow motion to show you this. So remember, when you launch it, right, you're going to have an X and Y component of the initial velocity. So you can see that there. And then the X stays the same, that horizontal velocity is staying the same, but the Y is changing, right? It's starting large, getting smaller, smaller, smaller. At the peak, it's 0. Let me do this again. So you can say at the peak, right there, it's all in the X, nothing in the Y, but that X velocity is the same as it was initially. And then after the peak, again, the X stays the same, but now the Y is negative and it's getting larger and larger in the negative direction until right before it hits. Okay, so that's what you need to do for that table. Let me go back to the lab handout for a second here. So again, fill in this table. Do a second plot on capstone. Again, you're going to plot range in the Y versus angle, which is in the X direction. Remember now range is in meters because this is in SI units. So it's a little bit different. Angles in degrees, but range is in meters as opposed to centimeters. And basically, you're going to do the same thing as you did before. You're going to fit a sine wave to your plot, and then using that coordinate tool, find the peak of your fit, the peak of your curve. And then I want you to compare the optimal angle that you found from your graph, so called the optimal angle experimental, to the optimal angle theory, which is 45 degrees, by computing a percent experimental error. And in question 6, compare the maximum range that you found from the graph to the max range theory. Well, how do you compute this? Well, remember, it's just going to be R max is V naught squared over G. In this case, your V naught is going to be 18, right? Because we had it set at 18 meters per second. So it'd be 18 squared, but be careful now, G is going to be 9.8. So divide by 9.8. And then compare that to what you got from the graph as your maximum range experimental. And since it's a simulation, these will probably be very close, right? You're probably going to get a very small error here when you compute the percent experimental error. Okay, and then there's one last thing I want you to do. So using the simulation, this is question 7. Set the bullseye target to be 20 meters from the base of the cannon. Keep the cannon at a height of 0 meters. And with the angle at 25 degrees, you want to experiment with this and figure out what the speed should be so that the cannonball hits exactly at the center of the bullseye. And then do the same thing for 45 degrees. So at 25 degrees, what is the correct initial speed to hit the bullseye, right, at a range of 20 meters? And at 45 degrees, what is the correct initial speed to hit the bullseye when it's at 20 meters, right? So let me go back to that simulation. I can move this out of the way. So here's the bullseye, right? So I can set this. So again, you're going to leave this at 0, right? I'm going to set this to be 20 meters. And then at 25 degrees, you want to figure out what the speed it has to be. So you just kind of play with this, right? If I try 10, doesn't do much of anything. If I try 16, oh, hold on. Let me do normal speed here. Ooh, actually, that's pretty good. That's too much. So you kind of have to play with it and figure out which speed is going to hit exactly at the bullseye when it's 20 meters away. And then do the same thing for 45 degrees. Okay, and then that should be it. So then work together, make sure everyone contributes, right, to the lab report. And then one person from your group will submit the lab report. We'll upload it to Brightspace under the assignment, right? We'll upload it under assignments. And then I'll grade it. I will assign the grades in Brightspace, so you guys will have the grades, and then we'll go from there. And then our next lab will be on Newton's second law. Now, I understand that this week is really like an extended spring break week, so you don't really have to start this lab until next week. So basically, let's see, on the 30th is really when you should start this. But if you want to get a head start, then go ahead and start working on it. Just make sure you keep the same groups that you had in the in-class labs. Okay, and then the other thing I'm going to try and do is from 10 to 11 on Monday and Wednesday, I'm going to try and hold some like online office hours through Zoom. So I'll keep that open, and I'll get you guys that information when I figure that out, exactly what I want to do there. But I'm just going to be available, so if you have questions, I can answer your questions. But the other way to do this is if you have questions, you can just email me as well. So if it's easier for you to email me, that's fine too. But I want to make some, some guaranteed sort of online office hours for help as well. Okay, well, good luck. Everything will be fine. We'll get through this, and we'll learn the rest of the concepts that we need to for the physics lab. Great.